online class. Okay, we are recording. All right, y'all. So what I'm doing here again is just showing everybody because the MyLab um, access that we got, we all did like for most of us, we did the temporary access. We got the 14-day free trial. Okay, so what's going to happen, y'all, is on Monday, at some point on Monday, when you click on the MyLab access, it's not going to send you here. What it's going to do is it's going to send you to this kind of a page. And what I did, y'all, just to, let me see so I can come back. Okay. So if you decided, like if you bought the code today and you want to go ahead and enter it in, what you would do, y'all, you would click on My Courses, okay? Now, mine is going to show up a few of them because I have multiple classes that have MyLab, right? So if you're in my online class, you click on this one here. If you're in the one that here meets in Westville, which is us, you would click on this one here. So if I click on this right here, that's not what I want to do. Sorry about that. Right here, upgrade access. So you would click on this upgrade access, okay? And I believe what's going to happen is when you get your code, or if you wait till it expires, it's automatically going to send you this page. Now, if you decide you want to buy it through Pearson, and guys, through Pearson, it is guaranteed to work. So one thing I just want to emphasize again, if you're taking Math for Teachers Part 1 and Part 2 right now at the same time, you're taking both of this semester, the $75 option one is great because you're only going to need it for this semester. Now, if you're taking Part 1 right now and you're waiting for Part 2 either until the spring or maybe the summer, then I would say do this one because then when you take Part 2, you'd have to buy it again, right? So if you can afford an additional 35 bucks, then get the this one here because it gives you access for a much longer time, okay? This one here is usually for 2 years. Yeah, it used to say up here we go, up to 24 months. And yeah, it'll be good for the 2 years. You know what I mean? So even if you decided to wait till next fall, so fall of 2023, if that's when you decided to take Part 2, you would be good there, okay? Now, guys, if you buy an actual access code, whether it be through like Amazon or you even go to the bookstore and buy one, what you would do is you would click on this part right here. And when you get that code, it's going to look something like this. It'll be like 5 or 6 letters, all the way through, and you would just enter them in. And once you enter all your letters, you would just click finish, and you'll be good. Now, again, I cannot guarantee you guys anything if you buy it through Amazon or eBay. The only thing I can tell you is that I've had students before who purchased it through Amazon or eBay, and they've never had any problems, right? But if you had a problem, can I guarantee you that it was like that we could resolve it? I couldn't, and I wish I could tell you that I can. But any student who ever has had an issue, they've been able to resolve it, okay? When you do buy the code, if you actually buy a code like through Amazon or eBay or even the bookstore, you're actually buying the 2-year code, okay? You're always buying the 2-year code. The only way you're gonna get the 18-week option is if you would have, the only way you're gonna get the 18-week option is if you actually select that one right there, okay? So again, just a heads up, on Monday, and it'll probably happen sometime Monday night, maybe even Tuesday morning. When you click on your MyLab, if you haven't yet bought the access, it's going to send you here, okay? And you won't be able to access anything until you either pay for the software or you just say, you know what, I'm not going to do any work, but I wouldn't recommend doing that. So anyway, just wanted to kind of give you a heads up. This is how you do it, right? Whether you decide to buy. And again, if you click on this one right here, it's going to send you to a page and you're going to just enter in your, you know, all your info. Guys, the only thing I would tell you to do is when you're entering like your credit card info and that kind of stuff, make sure that the address that you're entering in is the same address that's associated with your credit card. So if you recently moved out and you got your own place, but your bank information with your credit card company or whatever still has the address of your parents' house, then that would be the address that you want to put. Because if you're putting your new address and the bank doesn't know that, this part here is gonna give you issues. Okay, so just make sure you fix all that kind of good stuff. All right. And you can see, guys, the total order is exactly $100, $109.99. Doesn't look like there's any taxes or anything. So again, just wanted to give you guys a heads up on that kind of stuff. All right. All right. So let me go ahead and get out of this part here. And let me go back to my regular view. We can save that. Okay, so let's see. Let me come back over here, you guys. Today we are still in week 2. So today, y'all, we are going to go over section 2.2. I'll upload the lecture, y'all, by 5 o'clock this afternoon. I'm usually able to do it right after our class, so if I can get it done earlier, I definitely will. And then homework, y'all, is not due until next Wednesday. Friendly reminder, y'all, there is no class on Monday, right? Everything is closed here at SCC on Monday. That's why both of the assignments are due until next Wednesday, because we're officially closed on Monday, all right? So let me go ahead and get set up so we can go over section 2.2. And let me get my notes. Let's see, is that them? No. That's not them either. Maybe right here, maybe right here. There we go. This is what we're looking for. Okay. So let's see. Let me come back over here, y'all, and let's go over section 2.2, which is talking about describing sets. Okay. So it says students will be able to understand and explain set language and structure as applied to elementary math. Connections between finite sets and whole numbers. The use of one-to-one correspondence. Okay, so it says a set is a collection of objects which are called elements or members of the set. Okay, so there's ways that we can indicate a set. One way is a description, one way is what we call a roster form, and one way is we call set builder notation. So the first example here, it says, write a description of the set containing the elements January, February, March, April, May, June, July, August, September, October, November, December. Okay, so let me get my pen going here. What are we talking about? What are those? Those are the what? The months of the year, okay? So we're gonna say, okay, this is a set of the months of the year, right? It's just a description. Okay, let's do the same thing for part A. So here's part A. Does everybody agree that those numbers there are natural numbers, meaning they're starting with 1, 2, 3, 4, 5, so on and so forth? Okay, these are the natural numbers that are the first. How many natural numbers? How many numbers do we got up there? 7. Okay. The set of the first 7 counting, or if you want to say natural, because they both mean the same thing, numbers, right? It's not that difficult. It's just the idea of what are we talking about here, right? We're talking about the set of the first 7 counting numbers or the first 7 natural numbers. Okay. Okay, look at the next set, y'all. We have the set D. What are those? What are A, E, I, O, U? Anybody remember from elementary school? Vowels, right? Okay, the set of the vowels. All right, and I got one more here. Oak, maple, elm, pine, trees, right? A set of, I might say different, or even if I just put the set of trees, right? That's fine. Again, it's not going to be too difficult, right? Since we live in the valley, you know what we're going to put in here? You know, we live in the valley and we got a ton of those everywhere. All right. Okay, so a set is a group or a collection of objects. The objects that belong to the set are the elements or members of that set. And one method of denoting a set is simply to list the elements inside braces with the set of a capital letter. Okay, so y'all, just want to let you know, this here is what we often call roster form. Okay, roster form is just making a list of the elements of the set. Okay, sometimes that list stops, and sometimes that list goes on and on and on forever. Okay, so let me keep moving along here, and let's see. In the language of sets, y'all, so each element of the set is only listed once. So if there's a number or maybe a letter that belongs to a set that repeats, we only need to put it one time, okay? So we're only going to list them once. The order in which you put them in is not important, okay? Order does not matter. So if you put one element first and then another element second, or you switch them around, it doesn't make any difference. We symbolize that an element belongs to a set using this symbol here. This little symbol just means that particular element we're talking about belongs to the set. When we have that little symbol with a little slash through it, it means it does not belong to the set, okay? A set must be well defined. We must be able to tell whether or not an object belongs to a set, okay? All right, so here we go again, the roster method. So remember, the roster method, y'all, is just listing those elements. So here's my first set C, and it has the colors red, green, yellow, and blue. Here's the element N, or sorry, the set N, which are the natural numbers, 1, 2, 3, 4. Again, that means it continues, right? Y'all, does that set end, or does it go on forever? It goes on forever, right? So some sets are what we call infinite sets, meaning they never stop, right? Okay, and then here we have the set L, which we're calling the lowercase letters. Now, we have those dots there. Does that set end? At some point, it does end, right? What's the last letter? Z. So even though they have that, we really know that this letter Z is going to be in there, right? So even though they put the little dots, they're saying so on and so on and so forth, but we know it's going to end, right? So that's what we would call a finite set. Infinite means it goes on forever. Finite means at some point it's going to stop. All right. Another way we talk about sets is something called set builder notation, okay? Set builder notation, it's just another way of describing sets. And so set builder notation says the set C, which is equal to the set, the way I'm going to read this, y'all, I'm just going to read what I have right here. This is a set X of all elements X. That little line means such that X is an element of the natural numbers. It just means that X is a natural number and X is smaller than what number? Smaller than 5, right? So again, something we want to just think about, number, this means less than. Less than just means smaller. And when the arrow points to the right, that means greater than. And greater than is the same thing as bigger, right? Okay, so here's my first problem. And it says, write the set of the letters in the word woodpecker using the most concise method, where A is a set of lowercase letters. So let me explain what we want to do here. Okay? I'm going to write a set. It's going to look like this. I want to make a list of the letters that are in that word. Now, one thing I want to remind you all, the order in which I put the letters is not important. So I don't need to worry about putting anything in alphabetical order or anything like that. The other thing is, we don't have to repeat the elements if they repeat in the word. So the first letter I see is the letter W. The next letter I see is the letter O. Do I need to put O down again? No, right? We already have it. Doesn't matter. We don't need to put it twice. Then we have D. Then we have P and E and C and K. Do we need to put E again? No. But we need to put R. And that's all it's asking me to do. So notice, y'all, it says where A is a set of lowercase letters, use a comma to separate the answers. So if you notice between each of those letters, I put a comma. I used all of them with lowercase. And even though the letters repeated, I didn't have to worry about them repeating. Now, for part B, it says, write the set of natural numbers greater than 18 using the most concise method. What they're asking me to do here, y'all, is to write it something like this, okay? So look, I'm going to write my set, and I'm going to copy this first part directly. I'm looking at the numbers X, so that they are natural numbers. That's what this means. X is an element of N. That just means that X is a natural number. Remember what natural numbers are. 1, 2, 3, so on and so forth. And they are also what? Greater than what? 18. So I'm going to put and, just like I have over here, and we're going to say X. Look, y'all. Greater than means my arrow points to the right. X is greater than 18. And we're done. Okay. So all we're trying to do here, y'all, is just how do I write these different sets, okay? Let's see. Okay, we have something here, y'all, called a subset. It says A is a subset of B, and the notation we use is this kind of notation right here, y'all. And so it looks kind of like a little C with a line underneath it, okay? That just means it's a subset. And it just means that if and only if all the elements of A are also elements of B. So let's think about it this way. I'm trying to think of an easy way to sort of understand this. Suppose I had a big set. And let's see. We call that set, I don't know, mammals. Okay, mammals. Can anybody give me an example of a mammal? Anybody know what a mammal is? Dogs, right? Okay, so look, this could be the set of dogs, right? Dogs. Why? Because every dog is also a mammal. If I'm talking about dogs, I'm talking about mammals. Y'all, would this one, okay, would this one be in there too? Whales, aren't whales also mammals, right? So if I'm talking about whales, I'm also talking about mammals. But if I'm talking about mammals, it doesn't necessarily mean I'm talking about whales. This is the idea of subsets. One set is inside sort of a bigger set. So the mammals, I'm sorry, is kind of like this big umbrella. And then dogs and whales and cats and stuff like that, right? Those are all going to, cows, right? They're all going to fall under that kind of big umbrella. That's what we mean by subsets. Okay, so it says the symbol A is a subset of B, right? That's how I read this piece right here. I said the set A is a subset of B. So we have this symbol right here. Sorry, let me get rid of my email, guys. It's going to keep dinging here. Let me just close that up real quick. There we go. Okay, it says the symbol A of the symbol with a subset with a line through it is to indicate it's not a subset. Okay, so we say A is not a subset of B. And to show that A is not a subset of B, we must find at least one element in A that's not in B. All right, so let's go through these first 4 problems here to see if we can't figure out what are we trying to do. And the directions say, determine whether set A is a subset of B. All right, in order for A to be a subset of B, everything that I see in the set A also needs to fall in the set B. So question, I see boat here. Is boat here also? Yeah, right. I see train here. Train's here also. I see plane here. Plane's here also. That's all it means. So we would say here, y'all, A is a subset of B. Okay, because everything in A is also in B. Now, when I look at the next one, I see 1 here. Okay, I see 1 there. I see 3 here. I see 3 there. What about 5 and 7? They're not in B, right? So what we'd say for this one, y'all, A is not a subset of B, because we can find pieces in A that are not in B. Okay. Now, look at the third example. It says X is a yellow fruit, and B is a set of red fruits. So we want to know, are yellow fruits also under the umbrella of red fruit? Can anybody give me an example of a yellow fruit? Banana, right? Can you give me an example of a red fruit? Apple. Are bananas the same thing as apples? No, right? So again, here, y'all, for part C, I would say A is not a subset of B. All right, and we have one last part to go, part D. So let's do part D. I'm going to do it the same way. Time. Is time here? Yes. Newsweek. Is Newsweek here? Yes. People. Is people here? Yes. So we would say A is a subset of B. We're trying to make sure that everything in the first set is also in the second set. Okay. Now, there's something that we call a proper subset, okay? A proper subset. It says set A is a proper subset of B. Notice the notation for this one, y'all. The notation for this one here looks like this. It does not have that little line underneath, right? It doesn't have the little line underneath. And it just says if all the elements in A are also elements in B, but B has to have a little bit more than what A does, okay? So in order for it to be a proper subset, every element in A also needs to be in B, but B has to have additional stuff. So look, let's see if the first one works. I see jazz here, I see jazz here. I see pop here, I see pop here. I see hip hop anonymous, I see hip hop over there. But are there elements in B that were not in A? Yeah, there are, right? Classical and rap. So then we would say A is a proper subset of B. There's at least something in B that was not in A. Okay. All right. So now when I look at the second example, okay, so A is here, A is here, B is here, B is here, C is here, C is here, D is here, D is here. Okay, so I know that A is a subset of B because everything in A is also in B. But did the set B have anything additional? No, right? Okay, so we would say for this one, A is a subset of B, but it's not a proper subset. Okay, in order for it to be a proper subset, the set B would have had to have at least something additional. Okay. All right. So for the next problem I have here, y'all, it says rewrite the following using mathematical symbols. It says P is equal to the set containing M, B, Q, and D. Okay, so all we're going to do is this. For part A, y'all, we're going to write the set P, and we're just going to put those letters in there. M, B, Q, and D. And I'm just listing them. And all I got to do is just make sure that they're all there. The order of what I put them in is not important. So if we would have written the letter Q first, it doesn't make any difference. Okay. Now, for part B, it says the set containing the elements 3 and 7 is a proper subset of this one. Okay, so the first thing I want to do, y'all, I want to see if I can write the set consisting of the elements of 3 and 7. So I'm going to go like this. I'm going to write a set with numbers 3 and 7. Okay. And it's supposed to be a proper subset. So a proper subset, y'all, is just that little kind of funny looking C that doesn't have the line underneath. And it's going to be a proper subset of 3, 7, 8, and 12. And that's all I'm doing for part B. Again, I'm just writing it out. Now, we got a part C to it. Here's the part C. The set consisting of the elements 0 and 2. Okay, so I'm going to draw my set with the elements 0 and 2. Just look at that. The little squigglies and then 0 and 2 on the inside. Is not a subset. So, y'all, if that means it's a subset, then drawing the line through it means it's not a subset of the element or the set containing the numbers 2, 3, 4, and 5. Now, so we did the problem. I want to ask you guys a question. Does anybody know why the set containing 0 and 2 is not a subset of the set having the numbers 2, 3, 4, and 5? What's messing it up? The 0, right? 0 is not in the set containing 2, 3, and 4, and 5. So if 0 was in that second set and the 2, 3, 4, and 5, then it would be a subset, right? But that's why it's not. Okay. So for the next part I have right here, y'all, it says, suppose the set B is a proper subset of C. Okay, so again, I want to think about that for a minute. Suppose B is a proper subset of C. So that means B is a proper subset of C. Remember what that means, that whatever I have in B, I also have in C, but C has to have at least one thing additional. Now, the first part says, if the number of elements, the way I read this, y'all, real quick, just look at it. so we understand. The way I read this part, that's the number of elements in the set C. Okay, so let me write that right here on the side. Number of elements plus C in C. So if the number of elements in the set C is 6, then what would the maximum number of elements in B be? Okay, so let me think about that. If I were to say C has 6 elements, so to make it easy, y'all, this is what I'm going to say my set C looks like. 1, 2, 3, 4, 5, and 6. I could have done anything. I could have put 6 names. I could have put 6 letters. I just wanted to keep it simple. Now, we know that B is a proper subset of C. Okay, so that means if I write out my set B, everything that I write here has to be in that set. But the set C has to have at least one extra thing. So if I were to put something like 1, 2, 4, 5, and 6, right? The set C has to have at least one extra thing. What's that one extra thing? In this case, it would be 3, right? But if there's 6 numbers here, how many numbers could I have here? What's the most things I could have? How many numbers do I got now? Anybody know? We got 5 numbers, right? So the number in B, the most that it could be would be 5. It could be less, right? We could always have said, look, let's get rid of that number and now only have 4 numbers, and it's still a proper subset. But the most number of things I could put in here, the most would be 5. I couldn't put more than 5 things if the set C had 6. Okay. Now, there's a second part to that question, part B. I'm doing it over here, y'all, because I thought I gave us more room, but apparently I didn't. So look, B is still a proper subset of C. Okay. Oops. Okay, and it says if the number of elements in B is 6 elements. Okay, so look, let me think of again. I'm going to think of an example. I'm going to go A, B, C, D, E, F. Is that 6 letters? 1, 2, 3, 4, 5, 6. There we go. There's my 6 letters. Okay. So B is a proper subset of C. What's the maximum number of elements in C? Okay. Now remember, C is going to be a bigger set because C has to have at least one more. But it has to be at least one more. It could have 2 more. It could have 3 more. It could have 5 more. I could keep playing that game. So when we say, y'all, the number in C, there's actually no maximum, right? Sorry about that. There's actually no maximum because I could put all the letters, A through Z, 26 letters, but I could also start putting 1, 2, 3, 4, 5, so on and so forth in there as well, right? So C, if C is the bigger umbrella, there's no limit on what that bigger umbrella would look like, okay? So when I'm in the smaller umbrella, right, like in B, it has to be at least one smaller. But the bigger umbrella could always be as big as it wants to be. Okay? All right. The next part here, y'all, dealing with section 2.2 is something called a one-to-one correspondence. And it says, if the elements of the sets P and S can be paired so that for each element in P, there's exactly one element in S, and for each element in S, there is exactly one element of P, then the two sets P and S are said to be in what we call a one-to-one correspondence. Okay, so the easiest way, y'all, in my opinion, to do these problems here, it says which of the sets can be placed in a one-to-one correspondence. Look at the set A. The set A is the set of the numbers 1, 2, 3, 4, and 5. Okay. The set B, excuse me, is the set of the numbers, or the second set, I'm sorry, M, N, O, B, and R. M, N, O, B, and R. Okay. In order for there to be a one-to-one correspondence, all I got to be able to do is this. They match them up like this. And as long as everybody in this set gets paired up with exactly one person over there, and everybody in this set gets matched up with exactly one person over there, then we do have our one-to-one correspondence. Okay. So look, let's do the same thing for the second problem. So the second problem, look at the letters we're looking at, y'all. A, B, C. We're going to stop at F. What other letters do I need to keep writing if I'm going to stop at F? Anyone know? D, E, and F, right? So I'm actually going to write them all out, okay? Now, look at the numbers we're going to write out. We're going to write out 2, 4, 6, all the way to 10. So we're going to go 2, 4, 6, 8, and 10. And I'm just going to do this. I'm going to draw an arrow from here to here, from here to here, from here to here, from here to here. Is everybody getting matched up? No, right? F isn't getting matched up. So this is not a one-to-one correspondence, okay? It's not going to be a one-to-one correspondence, so yeah. All right, and so we have one last example here for the same part. It says, look at the set. It says T, so that T is a letter in the word can, and then my other set is the numbers 1, 2, 3, and 4. Okay, so for part C, y'all, what I'm going to do, I'm going to write down my numbers 1, 2, 3, and 4. How many elements are in the first set? For the T is a letter in the word can. How many letters are in the word can? 3, right? And they're all different. Okay. And again, we can see here, y'all, just by looking at this, there's not going to be a one-to-one correspondence. So this does not have a 1-to-1 correspondence, right? Right. So again, in order for there to be a one-to-one correspondence, I have to have the same number in the first set and the same number in the second set. Okay. All right. So the next part here, y'all, says two sets are equal if and only if they contain the same exact elements. Okay. The order in the elements makes no difference. So which ones we put first, which one we put second, not important. If set A is equal to set B, we write A equals B. And if A equals B, then every element in A is also in B, and every element in B is also in A. And if they're not equal, there has to be at least one element that's not in both. Okay, so first thing I'm going to do, y'all, before I do this problem, I want to talk about something called the empty set. The empty set looks like this, or sometimes we write a little 0 with a slash through it. This is just this. Sorry. This is just the set that has no elements inside it. Okay, there's nothing inside there. The set empty set is the set of no elements. So now what I'm going to do is I'm going to look at this problem that I got here, and I want to figure out which sets are equal. Okay. So I'm first going to stare at set A. Is there another set that has the same letters that A has, regardless of the order? What do you think? C, right? C has the same elements. Okay. So far, y'all, I would say A and C, they're going to have the same elements. Okay. So we got A and C done. Let's take a look at part B. Do you see any other sets that have the letters X, Y, Z, and W? No, me neither. Okay, so let's scratch that guy. We don't need to look at it. Let's look at the set D, y'all, just so we know what that set looks like. Okay, so number one, those are natural numbers. Remember what natural numbers are. 1, 2, 3, 4, 5, 6, 7, so on and so forth. When the inequality is written this way, it just means that they're going to be between the numbers 3 and 6. So if I wanted to look at the set D, okay, the numbers between 3 and 6 are 3, 4, 5, and 6. Now, I want you all to notice something. And again, this is something that we would have done in college algebra last semester or whenever you had it. I'm including the numbers 3 and 6, y'all, simply because those parts right there had the equal to. Now, if they did not have the equal to, then I wouldn't include the number 6. I would have say stopped at 5. Or if the 3 didn't have the equal to, I would have started with the number 4. Okay, but because it does have the equal to, I'm including those numbers. I don't see any other numbers with the numbers 3, 4, 5, and 6, so it doesn't look like I got to worry about that. Okay, now by looking at the next part, okay, remember what we call the empty set. There's two ways for me to write the empty set. It's the set with nothing inside it, or with the 0 with a slash. Looking at my sets, E, F, G, and H, are there any two up there that look like the 0 with a slash and the set with nothing else inside it? E and which one? E and H, right? So look, y'all, I'm going to select E and H. So this one here and this one here match up. Now, sometimes people ask, well, what about the set F? The set is actually a set that has the empty set inside it. Okay, so that's different. The empty set has nothing inside it. This has the empty set inside it. The set G is actually a set with one number, and that one number is 0. So there's still something inside there, okay? Now, I want to look at my two sets here for J and for L, okay? So when it says N is an element of W, that means those are whole numbers. I want to make sure that we understand what whole numbers look like. Whole numbers start with 0, 1, 2, 3, so on and so forth. The natural numbers, y'all, start with 1, 2, 3, so on and so forth, okay? So I want to look at those two sets, J and L, because I want to know, are they the same or are they actually different? I don't know. We're going to figure it out right now. So look, if I were to look at the set J, which has the numbers X, so that X is equal to 4N plus 5, and N is an element of the whole numbers. What would that look like? What I want to do, y'all, I'm going to do a little plug and chug. I'm going to come back to where my whole numbers are. Remember, the first whole number was 0. So I want to see what J looks like if I were to like make a list of those numbers. What's 0 times 4? 0. And 0 plus 5? 5. Okay, let's try the next one. We're going to use 1. What's 4 times 1? 4. 4 plus 5 is? 9. Okay, we're going to do this again. What's 4 times 2? 8. What's 8 plus 5? Anybody know? 13, right? Okay, guys, I'm going to ask you a question. How much am I adding each time to go from one to the next? 4, right? So after 13, the next one would be what? 17, right? So on and so forth. It's just making a list, just so I can have a picture of what's going on, okay? Now, I'm going to do the same thing we did here for the set L, because I want to know if those two sets are the same. And when I look at it, they look similar, right? It's not exactly the same, but they look similar. So look, the set L is the numbers that are equal to 4N minus 5, where N are natural numbers, okay? So I want to look at this set, because I want to know maybe L and J are the same. I don't know. So look, remember, natural numbers. Natural numbers, y'all, start off at 1. Okay, first question. What's 4 times 1? 4. What's 4 minus 5? I have $4, but I owe you 5. How much money would I still owe you? 1. Because I owe it to you guys, it's a negative. Yeah. Now look, I'm going to do the same thing. I'm going to do it one more time. 4 times 2. What's 4 times 2? 8. What's 8 minus 5? 3. Okay, I want you to look at this set here and that set there. Are they the same? No. So then the only ones that are the same, y'all, are the set E and H and A and C. Okay. But I didn't know if they were going to be the same or not. That's how I check to see if they're going to be the same. Okay, I'm gonna make a list so that I have a visual of what those numbers are looking like. Otherwise, I might say, look, one's a 4N plus 5, one's a 4N minus 5, but I'm starting one at 0, I'm starting one at 1. Yeah, that'll probably be the same. At least I want to know what those pictures look like, right? Okay, so I told y'all before, y'all, when we have that little N in front of the S, it's the number of elements in the set. We call that the cardinal number, okay? It's just the cardinal number. It's the number of elements inside the set, okay? So again, when I look at this part here, it says, what is the cardinality of each of the following? Okay, so look at my set K, 3, 5, 8, 0, and 11. How many different numbers do we have here? 5, right? 5 numbers, okay. How many numbers are in there? Just one, okay. Now, when I look at the set X, it's telling me, okay, X is a real number, and X is equal to X plus 1. Okay, so, and if you notice here, it says there's nothing in there, okay? I want us to understand why there's nothing in there. A couple of ways I could go about doing this. The problem says X is equal to X plus 1. Again, before we took the class, we all had college algebra. So we were trying to solve this equation, right? The first thing we might say is, look, I know that's a 1x, so let me subtract 1x here. I know that's a 1x. Let me subtract 1x here. So 1x minus 1x would give me 0. These would cancel, and that would give me 1. And is 0 equal to 1? No, it isn't, right? So we would say, okay, it's no solution. That's why there's no elements in there. The other thing is, look what this is saying. A number is equal to that same number plus 1. 2 is not equal to 3. 5 is not equal to 6. 10 is not equal to 11. That doesn't make any sense, right? It's saying that they are equal, but we know it isn't. That's why there's no elements in that set, okay? Now, again, that symbol right there, y'all, that's what we call the empty set. And remember, the empty set has no elements in there. So what's the number of elements? It's 0, right? Because there's no elements in there. All right. So let's take a look at the next one here. It says, find the number of elements in the set A when A is a number that's on a clock face. So again, y'all, all I did is drew a picture like this and put 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. How many numbers do we have on there? Anybody know? 12 numbers, right? 12 numbers. The number on the clock face, right? Okay. Look at the next one here. Find the number of elements for the set A. X is a natural number. Remember what natural numbers look like. 1, 2, 3, so on and so forth. And they are between 15 and 27. So y'all, this is what I would do. If I was sitting where you're sitting, this is what I would do. I'd go 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27. And all I would do is I would just count those numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 numbers. And again, all I'm doing, y'all, I'm just making a list. Why? Because I know what, if I know what this is telling me here, and I can get a visual of it by actually writing them out, then it's easier for me to kind of figure out what the problem is asking me to do. Right? Okay. So now, let's see. The number of distinct subsets. Okay, so the number of distinct subsets. So number one, distinct just means they're different. Okay, so it says the number of distinct subsets of a finite set A is equal to 2 to the power n, where n is the number of elements in the set A. And then we're going to have something called the number of distinct proper subsets of a finite set A is equal to 2n minus 1, where n is the number of elements in the set A. Okay, so let's take a look at this first problem here, y'all. The set A is the letters N, O, P, Q, R, S, and T. Okay, first thing I need to do, y'all, is I need to find the number of elements in A. Anybody know how many letters we have in A? What is it, 7? 6 or 7? 7, right? Number of elements in A is 7. Not 10. Sorry, guys, not 10 is freezing up. Okay, so to do part A, the number of subsets, we're going to say 2 to the power of 7. It's always going to be 2 to that power. Okay. So what I'm going to do here, y'all, let me grab my calculator. Depending on what kind of calculator you have, I'm just using this one here. Let me turn it on. Okay, and I'm going to clear this out. I'm going to say, what is 2 to the power of 7? And that's giving me 128. Now, the number of proper subsets, y'all, is going to be that same number, but minus 1. So if the first answer that we got was 128, then the number of proper subsets, y'all, is going to be 127. It's just one less. Okay, now to do part C, how many subsets does A have that include the elements P and T? The way you approach this problem here, y'all, is to look at the set that we had, which was N, O, P, Q, R, S, and T. And we want to make sure that we include the letters P and T. What you actually do, you guys, is you scratch those letters. Okay, scratch the P and the T. How many letters do I have now? 5 letters, right? So what we're going to do is we're going to say my answer is going to be 2 to the 5th. I actually scratch those letters, and then we figure out how many subsets do we have. So 2 to the 5th, y'all, I'm just going to take my calculator again. I'm going to go 2 to the power of 5, and I'm getting 32. Okay? If you're using a calculator kind of like this one here, it's just the one that comes on my laptop, right? Scientific calculator. What you would do is you'd hit 2, and then this is the power button right here, the little X to the Y. 5, and there's your answer. Same way, right? Depending on what it is you got. Okay. But that's my exponent button. Okay. So let me zoom in a little bit so I can take a look at the next problem we got here. Okay, it says on a certain Senate subcommittee, there are 5 senators: Anne Marie, Bo, Carlos, Dean, and Ellen. 3 of these members are to be appointed to a subcommittee. How many possible subcommittees are there? Okay, so what we're going to do here, y'all, I'm going to try to make this really easy. And look, Anne Marie, Bo, Carlos, Dean, and Ellen, I'm going to do it like this: A, B, C, D, and E. I'm just using the letter of the first name. Okay. What we want to do is we're going to make subcommittees of how many people? 3. So what I want to do is I want to list every possible combination of 3 letters. So we could do something like this: A, B, C. Okay. We could go A, B, and D. Okay. We go like this: A, B, and E. Okay. Let's see. What else can we do? We can say, look, how about if we go A, C, and D, A, C, and E. Okay. Let's see. So far I got 5. Anybody know any other combinations? Could we go B, C, and D? Can we do that one? Guys, if I did B, C, and D, what do you think would be my next one? B, C, and what other letter can I still use? E, right? Okay, question. Would I want to put something like, say, C, B, and A? No, because we already have those letters right there, right? The order is not important. Okay, so let's see how many we have so far. 1, 2, 3, 4, 5, 6, 7. Okay, I'm going to keep going. Any other possible combinations anybody sees that I haven't yet picked up? Have we done A, D, and E? Right, A, D, and E right there. What other ones? Do we have A, what else? A, D, and E, okay. Do we have B, D, and E? Okay. What else could we pick, guys? So we have A, D, and E. We have B, D, and E. Do we have C, D, and E? All right. Anybody else see any other combinations? You think we got them all? With 3? So what do you guys think? Can anybody give me any 3 letters? Just pick any 3 letters. I'm sorry, say it again. D, B, and E? D, B, and E. Okay, so look, just to make sure, do we already have these letters on there, just in a different format? Right there, right? Okay, so guys, all I'm doing, I'm looking for every single possible combination, right? And so in doing this, good guess, right? But that's how we do this. We try to figure out, okay, have we listed every single possible combination? And I believe we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm coming up with 10, right? And all I'm doing, guys, I'm just making a list. And I'm trying to find that with every single possible combination, okay? All right. Okay, so take a look here, y'all. It says, draw a Venn diagram showing the relationship between the set of natural numbers and the set of whole numbers. Okay, so we talked about whole numbers a little while ago. Does anybody remember what's the first whole number? 0, right? 0, 1, 2, 3, so on and so forth. Okay. Natural numbers or the counting numbers. What's the first counting number? 1, right? So 1, 2, 3, 4, so on and so forth. Okay. So everybody agree that both those sets go on forever and ever and ever? Which set is actually bigger? Even though one, I know they go on forever and ever and ever, but which set is actually, the whole numbers are actually bigger, right? And that means that the natural numbers are actually smaller. If the whole set, the number of whole numbers is bigger, that means the natural numbers have to be smaller. Which one of those pictures there has the whole numbers being bigger and the natural numbers being smaller? A, B, or C? Anybody know? But for, okay, let me ask you a question. Do you agree that every number here is also here too? So that means that the natural numbers, since they're smaller, they're going to be inside the set of whole numbers, right? So if the natural numbers are inside the set of whole numbers, aren't the natural numbers inside the set of whole numbers, right? And didn't we say the natural numbers is actually smaller? So when I look at my picture here, the N circle is smaller than the W circle. Why? Because the W circle has an additional number. It has one extra number. It's got 0, right? So guys, all this is saying is that N is a subset of W, right? Everybody in N is also in W. But not only that, it's a proper subset, right? Because W has at least one extra person, and it has exactly one extra element, being 0. Okay? All righty. Let me keep moving here. Oh, okay. That was it, guys. That was section 2.2. Okay. So again, the problems that you see here, y'all, are going to be problems very similar to what you have for your homework. And again, all we're trying to do is figure out the idea behind subsets, proper subsets, one-to-one correspondence, right? That kind of action. So that's 2.2, y'all. Let me go ahead and stop recording the lecture. Let me come back over here and let me stop recording.